Cool. Alrighty. I'm sure we'll have people flow in and out briefly here and then as we begin, but we'll just get it started in the interest of everyone's time. If you did just sit down, take a moment to sign in. I'll just do a little brief intro and then sign in, and then we'll get started. At the end, there is a sign out where you can basically tell me if I was terrible or if it was good, recommend topics, things you want to hear about in the future, that kind of stuff. I have a lot of people I know on the other side of that road there from all the different companies, and if there's a specific topic you want to hear more about, I can almost assuredly find someone to bring in and speak onto it. So keep that in mind, and hopefully that gives you some incentive to fill out the exit form and not just Jed. All right, everyone good? All right, we'll go backwards in time briefly. Wrong monitor. We'll go backwards in time briefly. So this is the first tech talk of the semester. This is not the first tech talk we've ever done. We've had this series going on for 2 semesters now, officially open to everyone. 3 semesters open to just Honor Society members and then other people. So my name is Ethan Hoban. I am the president of HKN, also known as Eta Kappa Nu, which is the Electrical Engineering Honor Society. Our chapter here is Theta Eta, UH chapter Theta Eta. And HKN is associated with, it's the official honor society of IEEE for anyone who knows what IEEE is, Institute of Electrical and Electronics Engineers. So today we're going to discuss radar discrimination techniques. We'll get to the disclaimer in a moment. We'll do a brief intro for me. So who am I? I am a graduate of UH here, the Electrical Engineering program. I graduated in 2023. I am younger than I look, I'm 24. I'm currently working on an electrical engineering master's here as well. My thesis advisor is Dr. Maria Poor. Electromagnetics antennas make sense considering the whole radar thing. I do have a full-time job. I'm a full-time Tempest engineer at Northrop Grumman. I can't specifically mention what program I work on, but you might be able to guess it eventually through the slide decks. Habitual project collector. I do a lot of different things. Word of advice for anyone, young or old, new or experienced engineer. Projects is how you win. You'll learn a lot in classes and you'll get pretty good at a lot of things, but nowadays most stuff is cheap enough that you can do it at home, or at least get an understanding of it at home. And let's just say I don't get jobs because of my degree, I get jobs because I put laser turret at the top of my resume. And it's a much better attractor and it helps. So we can get it moving on to the disclaimer. I promise this presentation is comprised entirely of open source information, primarily sourced from publicly available textbooks and journal articles. None of this is related to any work I have or will do with any customer or employer, I promise. Pinky swear. So, what to expect from this talk? Generally, we're going to first introduce what is radar discrimination, what are we talking about when we say that. I'll do a brief overview of radar operating principles in case anyone here isn't super familiar with how they work and kind of the types of radar that exist and the capabilities that already exist. Then we're going to discuss the concept of target characteristics. How does a radar make use of these characteristics? What can we determine from them, and how does the radar pick up on them? Then we're going to discuss advanced discrimination techniques, kind of some of the up-and-coming stuff that people have gotten into recently and for the future. Putting it all together, how to get into it yourself, where to learn more, and then brief bibliography. All that would be is just reference text that I used to compile a lot of this information. So, real basic, radar discrimination at the start. For anyone who has not had a history of radars, radar was first used in World War II, and all it could do back then was they would point the physical array of antennas in a general direction, and if they detected a return, they would simply know something is coming. They didn't have extreme precise information on how far or necessarily how many. They just knew if there was a stronger return, more things were coming, and they knew if there were a stronger return, it could also theoretically mean that someone was closer. And that was basically all they could do. Good early warning system, and it was extremely advantageous to the Allies, one of the 3 great technologies that helped win that war. However, nowadays, that doesn't really make the cut. Modern radars have to detect, track, and discriminate targets, And in this context, discrimination, when we're saying this, is simply picking a target out from its environment or other things. It could be other targets, but it's basically the ability to say, I'm looking at this thing and then continue to be able to track it and follow it, as opposed to looking at the environment, a tree, a flare, a jammer, anything like that. So you basically need to be able to say exactly what you're looking at and keep looking at it and not get distracted or confused. So this is extremely important. The modern battlefield is extremely complicated and it's extremely fast. This whole process here, the old end of the world process, when a nuclear missile launches, takes 30 minutes and is only really, at least most countries, can only really know what's going on in the latter 15. So you get 15 minutes to figure out what's coming and stop it. And even worse, it's not so simple. You've got things like chaff, you've got stuff that's designed to obfuscate yourself, your target, your system, whatever, from being detected. So modern systems have to be able to, near instantaneously, the moment something is detected, decide if it is a target, an ally, is this a jammer, is this a deception system, is this even a real thing? Is this a bumblebee moving at Mach 3, or is it an F-22? Like, what are we talking about, right? You need to be able to do this quick because you don't get a lot of time. And this is basically one of the most important things about modern radar. If not for radar discrimination capability, they would almost be useless. And again, I did briefly mention it there, and I'll mention at the end, we have a YouTube channel with all the prior recorded talks, including the prior talk I gave on electronic warfare. So if this in particular interests you, this brief slide, I recommend looking back at that talk. But on top of the fact that it's already complicated, you can actively trick and shield yourself with active jamming, barrage jamming, deception jamming, these types of techniques. And in the case of deception jamming, if you were unaware, you can literally generate entirely fake radar signatures that look like an F-22, an F-35, whatever you want. And not only can you generate it, you can make it appear as if it's anywhere in space. So you don't have to just mask yourself with a signature, you can make it look like there's just something out where there's literally nothing. That takes time, that takes effort, that takes resources if they fire something, and it's extremely problematic. So you need to be able to tell what's real and what's fake because everything's very advanced nowadays. So basic radar principles, hopefully everyone's relatively familiar with how this works. Radars in their simplest form is a fancy radio that transmits a signal and then receives its own signal back and uses the delay to tell, generally, how far something is away. And you can also discern things like speed, and then if you know where your radar was aiming, you can discern things like absolute position in space by doing some trigonometry, that kind of stuff. However, again, this isn't super helpful. I'm gonna do this one real quick. If anyone hasn't seen this famous video. So this is your old World War II crap that just scans side to side, if scans at all. And a modern system, you could be tracking 20, 30 targets all at once, near instantaneously, with what's called an active electronically scanned radar. That's what most modern systems involve. Instead of physically scanning, they use phase coherence and decoherence systems to just instantaneously steer a beam. So they have like thousands of little antennas and radios on board to do that. But there's a lot of different types of radars and they have a lot of different properties based on the mission. You could have something that's designed specifically to do weather tracking. You could have something designed that's specifically for early warning. So it's not extremely high fidelity, but it can see a really long ways away. In fact, we have systems that can see over the curvature of the Earth. And their sole purpose is just to do the same World War II technique of, hey, something's there. Task someone who's better at telling what's going on than me to exactly see what's going on there.
How does that work?
See around the Earth?
Yeah.
Radio waves can reflect off of certain parts of the atmosphere.
Okay.
So like if you're talking things like, ionosphere, troposphere, stuff like that, at the right time and angle and all this other stuff, and this changes. If you get your ham radio license, there's actually a lot about tropospheric propagation and ionosphere like reflection. But radio waves can and do propagate, reflect off the upper atmosphere and come back down.
Okay.
Yeah.
How inconsistent is that?
It can depend a lot. like an advanced system, it can be very consistent because they get the ability to just broadcast a huge amount of signal power. So even if they get a small reflection, it's enough. But for like a ham radio operator, like operating legally in legal power limits, it's not always a guarantee. So yeah, it can work, but also it can have problems. But basically, there's a lot of really crazy stuff. And with regards, and by the way, PRF, I think this is the only time I reference it. That just means pulse repetition frequency. Not all radars are, where it is, CW, continuous wave. Not all radars are constantly blaring a signal. Sometimes they just do a little pulse. So pulse repetition is just how many times they shoot out a pulse in a given second. Just for reference there. But there's a whole bunch of stuff. We've got satellites around the planet 24/7 that scan the entire planet every 24 hours. And generally, those are synthetic aperture radars, SARs. We've got stuff that does surface search from a lower, air search. We've got tracking. So tracking is normally like you're talking high fidelity fire control systems. They decide if the missile goes or not. You've got range stuff, weather stuff. We've got some really advanced spacecraft stuff. And there's a link I'll show briefly. We track like 30,000 objects around the planet at all times, including like wrenches that astronauts have dropped. And we do that with radar.
Question.
Yes.
Does sonar fall into that?
Sonar is similar
Okay.
in terms of physical principle, but it is using acoustics. It's using sound.
Oh, okay.
So, for example, a lot of the stuff we mention later on, specifically things like Doppler signatures, that's like the main principle behind sonar stuff. You don't get things like polarization and other tricks like that. And also you have significantly worse propagation with when it comes to acoustic energy versus radio frequency energy. But a lot of the math is extraordinarily similar, and a lot of the signal processing is also very similar. It's just that acoustics tend to be extremely low frequency, and radars tend to be very high frequency. So the physical processing of what's going on in physical structure in a sonar can be like really ridiculous. Like a sonar, like where a high frequency radar or radio, the antenna could be like, an inch, and you could, talk to someone in China. Not really, but enough power you could. But like with a sonar, you're talking like transducers that could be like the size of this screen. Like sonars can do the whole like 2 hertz kill everything at like a 2-mile radius type thing with the shock wave. But it's what's needed because sound propagation is so terrible, you need to basically use massive power pulses to get anything done.
Okay.
But, so target characteristics. This is where we're going to start discussing the stuff about a target that can be discerned and matters with regards to radars. So whenever I say target, it just references whatever your radar is trying to detect. It could be a plane, it could be this bag of tools that astronauts dropped in space. And just in case anyone hasn't seen this before, there is a website called Stuff in Space where they have a live map of every item ever dropped that is known of. And then you can click on any given item and it will generally tell you what it is. And you can even find all the objects from the launch, how fast it's moving. It would really suck to get hit by the 7-kilometer-a-second wrench. That would be unfortunate. Let me fix that. But yeah, so generally, and in the case something like this is a very important and yet more benign application of a radar. And that this isn't necessarily for weapon systems. I assure you we have radars to look in space for that purpose. But we have a lot of radars whose sole purpose is to basically give all of our spacecraft and satellites around the planet knowledge ahead of time that they need to adjust their course or get turned into dust. So I think the ISS makes like 50 maneuvers every day to avoid a collision. So,
done by them or someone on the ground?
as in like who puts the command in to move the thing?
Yeah.
I would assume the ISS astronauts control themselves, but realistically, it's most likely a computer doing it. I doubt they have to do anything automatic. The ISS, I think it's like a 5-kilometer keep out zone that they put around the thing in software, and if that keep out zone ever seems like it's going to intersect with any of those trajectories, they generally make a maneuver to not do that, ideally. I doubt they have astronauts on call just like running to things to be like, oh no, stopping it. That'd be a little inefficient.
Just a little.
Little, yeah. But here's a lot of things. Now, this is not necessarily an exhaustive list, And I wish I could say everything, but there are in fact many things that people keep close to the chest with regards to this because it's a discerning capability that governments or militaries make use of. But there are some very general things that matter. And when it comes to characteristics of a target, your physical size, how actually big you are, is a big component. Yep.
So for the physical size, what is the smallest thing a radar could detect?
That's a great question. Depends on the radar. But we have so-called ultra-high resolution systems. Now, generally, those are meant to be used as resolution along like the actual detecting axis. But things like a synthetic aperture radar, they are positioned all the way up in space. And you guys, I'll show a picture of what these things can do later on, but functionally it looks like it's a camera in terms of how high fidelity the images these things can take are. So like, it would really depend on the object, but detection normally comes down to two things. It comes down to like the wavelength you're talking about, because your physical frequency correlates to a wavelength. If your object is significantly smaller than the wavelength at play, you're gonna have worse properties to detect it. So you can go pretty high. Like there are radars that can operate at like 80 gigahertz, which is like centimeters, like minuscule sizes. But that's not the only thing, because then you need the ability to then receive it, and that's coming down to like your angular detection resolution. And again, like technologically, we could probably detect like sub-centimeter things if we really tried. Does it happen? It doesn't have a lot of benefit because something so high resolution would be really bad at most missions, because with such high resolution, then it takes forever to scan any type of region. But like for things like really small detections, again, like things like LiDAR are generally better at like really, really fine detection, but you could do it. So basically sub-centimeter, millimeter level resolution, you could get really tiny. But practically, most radars, you're talking like on the order of like meters or so resolution, because that's really all that was necessary for their mission. But, so physical size means what you think it means. It's how large you physically are. Obviously, a radar is going to have an easier job detecting a Boeing 737 as opposed to a bird. However, there are techniques, everyone's familiar with things like, stealth jets, that kind of stuff, where the bird and the plane may look similar in size. But that's a bit of a trick, right? And by trick, I mean it actually does work, but they're cheating a bit. If they had not done the whole stealth properties thing, the plane would be far larger than the bird. Shape is a huge component, and we're going to discuss in a moment the concept of radar cross-section and how that affects this stuff. But shape, and including in shape, we'll also discuss like orientation of the target relative to you. If you are a radar, and I'm on the ground here, little antenna, that's the general symbol for an antenna, and I'm projecting, let's generalize it as like a laser, even though it's not, it's going to be a wavefront. And I have a target that's just flat, perfectly perpendicular to my wavefront. Like, treat this as if it's a laser in a mirror. What's going to happen? Bing, bong, goes right back. Perfect. Well, what happens if it's like this? Bing, bong, off into nowhere. If the wave does not make it back to the radar, you do not detect it. Which, if anyone's familiar with the F-117's funky shape, that's kind of what they were getting at there, along with some other stuff like radar absorbent material, that kind of thing. Now we have better computers, we don't have to make polygon planes, but same deal. Shaping is huge. Shaping and viewing angle are extremely important as to whether or not a radar is going to be able to see you and pick you up, and it's also going to be important for like determining what you're looking at, because there's a bunch of information you can glean when a radar does hit a complex shape and you get a bunch of scatters back. You can do a whole bunch of stuff to figure out what you're looking at. Speed. Ideally, generally radars are talking airborne targets. I hope you're moving fast if you're in the air. Otherwise, I don't really know how you're up there. And it's important from a discrimination standpoint, because obviously we're going to classify things by how fast they're moving, because that can very quickly let us know what kind of threat we're talking about. Is this an ICBM or is this like a carrier plane, right? And then position as well. you're going to physically be located somewhere, and the radar has the capability to resolve that. But additionally, we will discuss in a moment the concept of like time histories, in that the radar doesn't just ping you once. The radar pings you, finds you, and then continues to do so over time. As it does that, it builds a map. It doesn't just forget the last thing it saw. It has a limited amount of memory, builds a map of what it's seeing over time, and can use that to be like, okay, this guy's moving in this type of trajectory. Our intelligence says this is similar to this type of vehicle, yada, yada, yada. And they start to break down who we're looking at, right? And these characteristics can be and are detected by radars all the time. And then we're going to use a whole bunch of fancy techniques and signal processing to extract as much information out of these characteristics as possible. And you can do some pretty ridiculous stuff and ultimately classify what we're looking at here. So we're going to go from the actual characteristic and how the radar actually can extract this data and what it's seeing. Physical size and shape are extracted in a similar manner. The radar will send out the wavefront, send out its signal, it'll refract and diffract and reflect back, and you will get the radar return strength, which is just how strong the signal is in terms of watts. And then you're also going to get things that are features of a return. And this is going to come out in a moment, we'll discuss that, and this is called radar cross-section, and there's a whole bunch that comes out of this. And then things like speed, is everyone familiar with the Doppler effect? The old ambulance comes towards you high pitch, leaves, goes low pitch type thing. That is how we discern speed, and it's also how we generate Doppler signatures, which are a really great way to figure out what you're looking at. And you'll actually be pretty amazed at how precise the Doppler signatures can get. And then position, you're coming off of time delay. That's the general method of determining range. And angle of receipt, you know where your radar was looking when you sent out a pulse. If you then know that angle, and then you know how far something is, you just do trig. And now you know where you are, or where your target is. So, physical size and shape. This right here is an image from this glorious book. If anyone in this talk, during this talk, gets really interested in stuff like radar cross-section and that kind of stuff and stealth, this is the book for you. Radar and Laser Cross-Section Engineering by David C. Jean, 3rd edition. Runs a pretty penny. I think it's about $120. Probably get it used for $80. But it really is kind of the Bible for this stuff. And it's entirely open source and unclassified. So you're fine to just purchase it and learn what you like. But this figure is very helpful. It shows just like a standard plane-esque complex geometry. And basically, the target size and shape is discernible by the radar by the strength of this return. But the return is not simply a signal with some amplitude or level. It could be, but that would not be all that useful. Generally, when the return happens, you're not just going to get one single return, because if we, again, think of this as a general wavefront passing over, let's say the radar is all the way over there, sends a signal towards the nose cone. Well, it's going to hit the nose cone first, and it's going to start going back, but it's not a laser, it's a wavefront, it's going to keep moving. Then it's going to hit this inlet duct, do its thing, start going back, it's going to hit these wings, do its thing, start going back. So from one send of your signal, you will get multiple returns. They're all going to be different times. They're all going to be different like time delays from one another. So you can do things like resolve the length of the target. Okay, I got return 1 here, then I got return 2 here. Return 2 is not characteristic of a specular or reflection. It's characteristic of an edge diffraction. What does that mean? That means I know I got my first return, and that's the nose cone. Got my second return, that looks like a wingtip return. Now we know the length of the vehicle. Now we can start eliminating who we're looking at. Okay, Boeing 737, too long, can't be that. Oh, that kind of stuff. So you're starting to kind of get the picture of what I'm getting at. There's a ridiculous amount of information you can pull from this, and a bunch of it is classified, I'm sure. But not this, though. So I will discuss briefly what's going on here. Let me make sure, what's the next slide? Yeah, okay, good. Don't be worried, we're not going to discuss that math I just showed. But it's not as simple, right? You're going to have things like, you're going to have a bunch of different frequencies come through because there's going to be varying Doppler effects that occur, and we'll discuss that more. But there's also a whole bunch of effects here, like creeping waves, ducting, edge diffraction, surface waves, that kind of thing. So when you guys think of like a radar hitting, or just a radio wave hitting something, or electromagnetic wave, a lot of people generalize the concept and try to treat it like it's a, light and a mirror. It reflects and that kind of thing. And the geometric optics approach is helpful in quickly understanding things and approximating things, but it won't really cut it. When a radio wave hits a conductor, or really not even necessarily a conductor, but at minimum a boundary condition, which is just a change from one material to another, which could be as simple as free space to a metallic body, it will then generate a current in the body. So the wave has hit it, the current is then generated in the body, and then the body becomes a new antenna, and then re-radiates that wave back out to space. And it can do it in numerous ways. So there's concepts like surface waves, where it hits, gets absorbed into the surface, the current flows along the length, can come back and then re-radiate out. So this can be a huge problem. And again, this is why we have things like stealth technology to minimize as many of these effects as possible, because some of these can get really bad, as in you light up like a Christmas tree and there's very little you can do about it. Particularly inlets, they're terrible. Ducting and waveguide modes will ruin your life. That's one of the reasons that if you look at something like a B-2 Spirit bomber, where it's inlets on top, and where are planes generally? In the sky. So ground-based radar, what does he see? Flat bottom with no inlets. Simplifies the fact of not having to deal with this problem, because it's a huge issue. And when we talk about Doppler in a moment, you'll see how much of a massive issue it becomes beyond just reflections, but because of Doppler, micro-Doppler signatures as well. But as I say here, you're going to have the final return is going to be a composite of multiple signals with differing arrival times, magnitudes, frequency. Yep.
So, are you familiar with NCTR, non-cooperative target recognition? Takes a look inside the underside and gets into the fan ducting. I always wondered how that works.
That's a micro-Doppler.
Yes.
Yeah, it's a micro-Doppler signature. I didn't know it had a name. What would you call it?
NCTR, non-cooperative target recognition. I just know that's the term used in, I think, since the 80s for like American fighter jets.
Yeah, that would be classified as a micro-Doppler signature. And there's a couple other things, but we'll get to it in a second. But it's good to know that it has an official name besides what I thought it was. Thank you. But it's not as simple, so it's got various arrival times, magnitudes, frequencies, and polarizations. And we'll discuss the concept of frequencies and polarizations briefly. Frequencies is covered by Doppler, and polarization is a separate topic. These composite signals can be received, processed, broken down, and turned into a unique fingerprint. So the full RCS profile, again, huge, important. Like if you right now pulled up Google and you said, hey, what's the radar cross-section of an F-22? It'll give you a number. It's probably wrong, but it'll give you a number, right? And maybe if you hit Google Images, it'll give you a fancy 2D plot. Circular plot that's got like 0 to 360 degrees. And then it'll also have, as you go out farther from the circle, it'll be like magnitudes, generally in something like dB. Radar cross-section, generally, for the uninitiated, they'll just say square meter. Oh, it's radar cross-section's 1 square meter, right? In reality, that's not the actual unit. The actual unit generally is dBSM, decibels per square meter. So it is still a corollary to area, which is, again, physical size. But this is important. Radar cross-section is never just a number. That's what they tend to do. They just say, oh, it's this. But that's not right. Radar cross-section depends on the aspect angle that you're looking at the vehicle. Basically, if I shoot my radar away from here, I'm going to get a return. But what happens if I hit it from behind instead? Different return. Which means every single angle in all 360 spherical degrees to radians you could look at it from, it's going to have a completely different return. So the actual answer is, for any given vehicle or system, it will have a full all-aspect spherical return per frequency of interest. So you can't even generalize it across all frequencies. Each frequency has its own entire full 3D signature that you have to understand. And that's why only a couple countries have the capability to build stealth vehicles, because it's extremely expensive to validate that and test it. There's only a couple radar ranges on Earth that are capable of doing all these types of measurements, particularly for the fact that a lot of them can measure the actual vehicle and not just a scale model. Like, for example, I think who is it? Navair up in Maryland. They're one of the places I know can do it. Maybe White Sands might do it. I don't know. Someone else probably. But so, talked a lot about this. This is a massive topic. You could have a whole career in this. I work with several people who this is all they've ever done their whole career. It's a whole thing. If you're really interested, I do recommend getting the book. Real quick, we're not going to actually go into this, but this is the received power radar equation. Whenever we're talking radar, sigma is radar cross-section. That's all that means. And as you can see here, the received power scales linearly with how big this number is. So as mentioned, bigger physical size, generally bigger radar cross-section, unless you get clever, apply radar absorbing material, shaping, deception jamming, coverage jamming, that kind of stuff, your radar cross-section can drop. But generally, if you don't do anything fancy, as you get bigger, that number goes up, you become more detectable. Speed. Simple, everyone loves the ambulance example. As you move away from an observer, the wave stretches and becomes lower frequency. And then as you move towards an observer, you will compress the waves and you'll get a higher pitch. This works in acoustics and this works in electromagnetics. Pretty cool. Another instance of those maths being extremely interesting or very similar. But this one's particularly problematic. So, radar cross-section can be mitigated by stealth techniques. It is extremely difficult to deal with Doppler effects. There's not really a great way besides deception jamming to mask how fast you're going because that's just a physical property of your existence. So if the wave hits you, doesn't matter how low your RCS is, they will still technically see a very small blip moving at Mach 2. And that's the whole bumblebee moving at Mach 2 joke that you may see on the internet sometimes. But it's a true thing. Now, generally, most radars are not automatic, entirely computerized systems. They have operators. And one of the benefits of stealth is that it makes it really hard for the operator to do their job. Generally, they miss it. Even if it is moving fast, filters, operator error, these things result in our systems being able to get past and do their mission. But it's very hard to mess with these, or mitigate these Doppler effects. The Doppler effect does not only will allow you to discern fast-moving targets from the environment, which is extremely useful because generally, relative to the radar, the environment is stagnant, it's not moving. So you can very easily and very quickly figure out what's going on. But here's another interesting concept. Back to this picture. In space, where there's no air, the RV, which is just a reentry vehicle, if anyone's ever seen it, looks like just a cone. And chaff, does anyone know what chaff is? Any chaff knowers? What do we got?
Small metal flakes in the air that spoof and mimic radar returns, right?
Yeah, so chaff is, as you mentioned, basically small metal flakes. Think of it as literal confetti, just like absolutely made of metal, metallic. And how it works, just like any general piece of metal, is it will reflect radar really good. So chaff's been around forever. World War II, they figured it out. And basically what it does is it makes it really hard to tell what's going on inside the area. They'll know something's there because the chaff is there, but it makes it really hard to discern what's going on. But what happens when small metal flakes hit the atmosphere? They do burn up, but before they burn up, they slow down. So when they're in space, these guys move at the exact same speed. The moment they hit the atmosphere, the chaff starts to slow down. So even though it's giving a massive return, its Doppler signature has just changed. It's moving slower. The moment that happens, it's useless. Now they know there's an RV there and they can track it based on its Doppler signature.
Oh, but it's too late at that point.
No, not quite. I agree it's unfortunate, but it's not too late.
Yeah, it's really close.
There's historically there's many more, but generally we'll just talk about the Russians. The Russians have a BMD system, ballistic missile defense system, just like we do. Ours is designed to do stuff up here. Theirs is designed to do stuff down here. So they literally just, they shoot a nuke and a nuke. That's their shtick. Now, to be fair, we did that back in the day too when we were uneducated, but we got a bit better about that. They still do that. But yes, the atmosphere starts at about 350,000 feet. So you still have plenty of time to commit to an engagement at that altitude. Once you start getting lower, even back in the day, the American Sprint system, Sprint missiles part of the safeguard system, that was designed to engage at 50,000 feet. So it can still be beneficial, particularly as modern nuclear weapons are far smaller than they were in the past. We're not talking megatons anymore, we're normally talking 300 kilotons. So it is worth attempting it. But I agree it's unfortunate, particularly because it's highly unlikely that there's only one of these things coming at you. And there's a lot of treaties that restrict how many systems you can have.
Well, metal or whatever is usually used for the chaff.
Which metal
Yeah,
specifically?
what material?
I'm sure that's classified,
Okay.
but generally,
I figured, but thought I'd
generally, reflective, non-ferrous metals. So from an electromagnetic standpoint, you have two operating modes. You have electric and magnetic operating modes. Magnetic is normally near field. Electric is far field. Radars and most long-range systems operate in the far field region, which is predominantly dominated by the electric field. So out there you want non-ferrous materials. You want things, basically just whatever non-ferrous metal pops to your head is probably a good candidate. Ferrous materials, not only are they generally heavier, but they don't work as well because they're generally better for lower frequencies and magnetic regions, so close range stuff. Let's get back to where we were. Here, yes. So, yes.
So kind of random. I one time heard a rumor that the military buys a bunch of, glitter or something like that for chaff? That was a rumor I heard.
It was never confirmed who buys the glitter in mass quantities. It was just confirmed that there is someone who does it.
Okay.
But I know what you're talking about.
Okay.
You mentioned, earlier when you were talking about the Doppler shift, how you can't prevent it, you said there's no great way to prevent it besides deception jamming? What is that?
So deception jamming is a type of electronic warfare. And I mentioned it briefly, and I did a talk last semester on kind of more how it works. That is recorded, so I can send you the link so you can see more about it. But quick overview, by deception jamming, they send the radar signal at you. You have a fancy schmancy antenna and receiver system. You receive it instantly. And the way these systems work, they don't even use computers most of the time because computers are too slow. Because we're talking light speed, near light speed operations here. So what instead you generally use analog delay lines, phase shifters, stuff like this. And the purpose is their signal comes in because generally, I didn't mention this because it's not necessarily important to discrimination. Radars generally, advanced modern ones, tag their signals. So it's not just a sine wave, they're modulating and putting unique data identifiers into these things. So you can tell that you're listening to your own signal. It helps with that stuff like that. But you receive the system, you receive their signal, you make tweaks to it, you introduce a delay, you introduce a phase shift, a polarization shift, amplify it, magnitude shift, whatever you need to do. And by tweaking these parameters and then sending it back to them, you can create false signatures that could literally look like a completely different vehicle made of completely different materials in a completely different location. Moving at a different speed as well if you want. But that only works if your radar cross-section is low enough that your return that you fake send them is bigger than your own return, otherwise it won't help you very much. But that's how modern stealth vehicles work, because stealth alone is not enough. Modern radars are too good. You need to have something that covers your tracks while you're doing it. So almost all systems, F-35s, F-22s, whatever you can think of, they have advanced electronic warfare suites on board. The F-35 has a towed deception jammer. So they release a physical device out the back connected by a fiber cable, and they use that to try and trick it. And at worst, they make the missiles go towards the thing that's not the plane to stop it.
Wow.
Think of it as a radio flare, but way fancier. But it's pretty cool stuff. But there are other issues. Not only will it allow you to discriminate fast-moving targets from the environment, which is extremely beneficial, but it also allows you to further classify and fingerprint stuff based on so-called micro-Doppler signatures. And this is where it gets a little ridiculous. But before I talk specifically about that, I want to make a clarification. This picture really makes it look like you have to be physically progressing at a high speed towards the observer, in this case that would be the radar, or in the opposite case, moving away from it. That's not necessarily the case. In fact, you could be moving, radar's here, we're a fixed distance away, I could be moving like this, and that will still generate a Doppler signature. And that's where this microsignature stuff comes in, because it's really problematic. So as long as it's moving relative to the radio wave, you can generate a Doppler signature, and it doesn't mean you have to be going right towards or away from a target or a radar. For example, if you aimed a radar at a fan that's stagnant and sitting in front of it, but the fan blades are rotating perpendicular to the radar, it's going to pick up the Doppler shifts of each fan blade as it moves. And that's the so-called micro-Doppler. And once you've heard that that fan thing exists and you start thinking about how turbofan engines work, you start realizing where this is going. And even worse, vibrations themselves can generate Dopplers. So if you have a piece of equipment in your airplane that wasn't tied down very well, it can give you away. Or at least help them fingerprint you. So this right here is from an IEEE paper. Big thing, all of you as students of UAH have free access to IEEE Explore, where think of it as super Google. You can basically Google or search anything you want through the library. You can just log in, and it's going to give you thousands and thousands of research papers that normally cost a lot of money, and they're extremely helpful. I highly recommend just kind of getting used to using it as a resource, because it's a really great way to pick up on like cutting edge information really fast. But in this case, this guy's just doing a whole bunch of stuff. Jogging, throwing a stone, crawling, jumping with a gun, I guess, army marching, whatever. And the plot here is time versus frequency. Because what is the Doppler effect? It's not necessarily a change in magnitude, it's a change of frequency. As you move towards it, it increases frequency. As you move away from it, it decreases it. Well, as we can see, you can create what amounts to unique maps of different movements or different parameters. In this case, it's a person, but vehicles are loaded with moving parts, funny enough, including people, which is a really interesting thing you can do. But as you can see, this could get pretty ridiculous. Now imagine this, but instead of using what's obviously like a $30 radar, no, probably more like a $200 radar to make this paper, imagine it's like a $300 million long-range discrimination system, and you're gonna start to realize, okay, this thing can kind of just see anything, right? And is there any confusion about this, like what's going on in these pictures? Because I can describe it a bit more in depth. Or does everyone kind of get the gist? Frequency component goes higher. And then the heat mapping, that's just gonna be like magnitude intensity of return. And then wherever the map appears is based on the frequency components, right? So you'll notice, and this is a fun quirk, repetitive actions, particularly repetitive linear actions, if you really look into this, you see the sine wave. Because that's really all that is, which is cool. Position. As mentioned, this one's quick. Radars make use of time delay between transmission. So this time delay can be used to tell the range of something. But when we talk about the advanced discrim in a moment, you'll realize that it's become far more useful than merely saying how far the physical target is away, but rather it can also discern like the actual physical sizes, lengths, and a bunch of other features about the target, which we did mention a bit about with radar cross-section. But as mentioned, you make use of the known angle where you're looking, and you can basically triangulate where a target's located. This one's pretty basic. In terms of discrimination, position itself, like a single instance of position, is not super valuable. But as mentioned, it's never a single reading. It's going to get you again, again, again as you move. That trajectory and time history starts to build. That is of value and can be used to figure out what's going on. Because a missile is going to move different than a plane moves different than a helicopter moves different than a spacecraft, right? Polarization. This one's really crazy, and it can be a little complicated if you don't have an EM background, but basically, when an electromagnetic wave is generated based on the position and geometry of the antenna, it will impart what's known as an polarization. And all polarization is is, so electromagnetic waves have an electric component and a magnetic component. They're always perpendicular to one another. The definition of polarization is where the electric component of the electromagnetic wave is pointed at any given time. So in a linear polarization case, what's happening is the electric wave is oscillating back and forth in a line. So in this case, if you were to look at it from like the front or the rear, its oscillation would just look like a line. It would draw a line on the graph, right? Circular polarization, you can see it, the line is basically rotating about an axis as it propagates through space. So if you look at its map, it just looks like a circle. Looks like a line drawing a circle over and over again as it traverses. And then elliptical polarization is just the general form of circular. Circular means that it's perfectly in magnitude in both directions. Elliptical is far more realistic. In one direction it's going to be more dominant than the other, so when it draws, it's going to trace an ellipse. You don't really need to know too much about this. What you do need to know is that polarization is generated when you transmit, but it doesn't mean you get the same one back, and that's useful. So, radars can have an inherent polarization, and by can I mean do. But more modern ones can do fancy stuff like change their polarization at will, which is very expensive but very cool. And based on how the scattering of the target depolarizes, aka that just means changing the polarization of the signal, the radar can further fingerprint the target. Specifically, it can fingerprint things like material properties. Different materials depolarize in different ways. So if you're trying to probe what's going on, the radar could send, okay, let's go linear polarization first. All right, now let's hit circular. Now let's do elliptical. And then you can do that, and when the return comes, there'll be changes in polarization such that you could be like, okay, this change in this linear polarization at this frequency is consistent with this composite we know is used on this aircraft. So we're starting to, again, bring our decision down and down and down until we figure out who we're looking at. Because ultimately, again, the whole point is to figure out what we're looking at. So this one can be a little confusing, but being able to determine the materials that you're looking at can get pretty useful. Particularly, and I hinted at this briefly, but when it comes to discrimination and classification, well, you need to know what you're looking for. So your discrimination is only as good as the intelligence you have on what you're looking for. So the United States and various countries have massive surveillance operations going on 24/7, whose purpose is to pick up on this information so we can make use of it in a battle scenario. So we've got people whose sole purpose is to, any time a Russian plane flies in the sky, we're pointing 7 radars at it to get as much data as we can to build these maps. So if we ever need to use it, we can discern what we're looking at quickly. And that goes for everything. Submarines, boats, ships, whatever you'd like to talk about. And that doesn't just mean we do that for just radar. You know, we're in a world where electro-optical and infrared systems are becoming very prevalent. Everything we've discussed here is done in that regime as well, just not exactly the same way, because obviously there's different physics at play. But the whole point of polarization, you can further fingerprint the target based on its material properties, which is very useful. Oop. And this is the concept of, you can have a linear vertical polarization, is just doing this, propagates through a medium, in this case that would be a new material, and then is reflected or transmitted, and now you've added a new polarization, it's shifted it somewhat. And you can make use of this. All right. We're moving on in the interest of time to advanced radar discrim stuff. So this is kind of just more of like where the future is headed and some other like really crazy stuff that we can do with radars. Everything I've discussed thus far has been in play for a long time. We've improved it drastically with new computers, new antenna systems, new radios. So we've been able to advance the capability, but the underlying idea is the same. Doppler's been around forever. Like, these concepts aren't necessarily new. We've just been able to like push it to the extreme. However, there is stuff that we've been kind of pushing that's really cool and has some really interesting applications. So I mentioned earlier the idea of being able to determine the length of something because of like the return delay happening. So the pulse traverses poles, and then there's going to be 2 time delays that can give you lengths. But as per which question? I think it was who said the smallest? You. Yes. So the smallest resolution is dependent on the system. Most radars don't really care to go super, super fine. They just need to find like maybe a 100-meter area of where something is. This type of system, known as a high resolution range, well, it's a high resolution radar, but this type of profile is called a high resolution range profile, is an advanced capability that allows the radar to produce a one-dimensional image. So what this means, let's say the radar has sent a signal and propagates from this side of the boat to the other side. This is in meters, and this is in scattering coefficient, which is just decibels, so it's return signal power level. They have such resolution and such fine signal discern capabilities that as the wave, again, speed of light, propagates over this, 60 meters, so it's like, I don't know, picosecond, just almost instantaneous. They can pick up, to meter resolution and sub-meter resolution, every single different return and its time delay, which allows them to then, based on the physical features, mass there, mass there, mass there, bigger mass there, some stuff here, here, and here, generates different spikes. And these spike maps, again, just like radar cross-section, are highly dependent on where you're looking at the vehicle from, but the maps can be used to directly determine, oh, this is that kind of vehicle, or oh, this is this kind of ship, missile, whatever. So this is some really crazy stuff. And if you want to learn a lot about it, excellent text here, high resolution radar. It's from our tech house, so they're going to take your mortgage if you want this book, but it's good, it's worthwhile. You can probably get it on eBay for like $30 if you really try. But this is a good one. Then, kind of push it up. So this is the last advanced discrim slide. I don't want to push it too long, but advanced discrim, concepts like SAR, ISAR, and AI, obviously AI's been around for a while. Now it's getting more famous because ChatGPT exists, but of course, in a world where you're talking about classifying information and discerning things, one would assume AI is fairly useful. So they've been doing things like neural networks and AI to help with automatic discrim for a while, but now they're just pushing the limits because you got more people in the field, it's helping out. So that's a big area of where we're headed, but don't get me wrong, there's still gonna be a whole bunch of, time and money spent on just refining the actual underlying capabilities still, because there's a lot, we can still push it. However, who here is familiar with SAR and ISAR? So we got some SAR and ISAR. So these have been around for a while as well, but we've really started pushing the capabilities. So what these stand for is synthetic aperture radar and inverse? It is inverse synthetic aperture radar, yeah. Inverse synthetic aperture radar. And basically, if I told you that was a picture from a camera, would you believe me?
Yeah.
Yes.
Oh, it looks pretty good. Well, it's not, it's a radar. So that's the shtick. We're long gone are the days where, you send out a radar pulse and it comes back as a blip on a screen. It's basically a super fancy long-range camera. This image was like near revolutionary back when it was made. And then there was a more crazy one recently where they imaged like an asteroid out near Jupiter or something obnoxious with a synthetic aperture radar. When this is synthetic aperture, this is inverse synthetic aperture. And they basically explained it as using a lens the size of a human eye to take a picture, like in San Francisco, to take a picture of a car in New York. That was like the scales at play. So the shtick with things like SAR and ISAR, the whole point of why these are crazy is these resolutions are insane. Like you're looking at this and it looks like a picture, to the point where why even use a fancy signal processing technique if you could just take a picture and run it through a computer vision model, right? And be like, oh, okay, well, that's a MIG, right? Obviously. But there are limitations currently, things like SAR and ISAR. And by the way, so ISAR always is characteristic with the, looks like a thermal map. But what this map actually is for radar return strength. So ISAR is extremely common to actually help people figure out the radar returns of something. So this helps you design a stealth vehicle. you can use ISAR imaging to visualize the radar cross-section of something. But how these things work relies on motion, and unfortunately it's weird. SAR relies on the physical motion of the actual radar itself in order to do imaging. So it basically scans. So instead of the radar basically like turning or using phase where it sits there and just spin or steers its beam electronically, synthetic apertures have to physically stay looking and just move. They're often mounted on planes or satellites. So this lets you do this vision, but it does not let you like figure out what's going on. However, ISAR does, predominantly used for maritime applications, but it relies on repetitive movement of the target. Hence maritime applications, if you're a boat on the water, waves are they oscillate and it helps you make these images. But we're pushing a regime where we're gonna eventually have systems that basically look like they're taking pictures, but it's a radar. So that's pushing the fidelity to the point where like, your operator just needs to look and be like, yeah, it's a plane, and then just, take it out.
So is that picture on the right, is that what the radar has, that's basically the picture has the radar to it? So that's like an object?
That's a planet, I think. But I think it's like Mars or something.
Oh,
or a
okay,
moon.
okay, that makes sense.
Yeah. I don't remember which moon,
Yeah, okay,
but yeah, it literally looks like a picture,
yeah, okay.
but it's a radar. And similarly, this one also looks like a picture. Fancy colorized picture, but a picture nonetheless.
Is that colored when it takes the picture too, or is that?
Oh, absolutely not, no. We make
That's
that
what
up.
I thought.
No, of course
I
not.
was like,
Now, they have used polarimetry to decide what to color things, because again, polarization can tell you material properties,
oh, yeah,
but it doesn't like actually make a color. You gotta add that in software later.
okay, I figured. Yeah.
But like, so SAR is what we use to image the Earth. So very recently, I think like a month ago, NASA and the Indian Space Agency launched a satellite. It was called NISAR, NASA India, synthetic aperture radar. And that system is up there. I think it was renowned for two reasons. It was like the first like largely successful cooperative action between NASA and the Indian Space Agency, but it also had like a ridiculous radar fidelity that it had a specialized antenna reflector that it unfurled as if it was like a solar panel and made like this massive 30-meter antenna cage. And yeah, anything you see publicly like that, just know like who's my favorite spy agency? Which one is it? I don't remember. It's not Geospatial Intelligence Agency, it's the other guys. I don't know. There's someone who makes all those spy satellites, and they've been far better for far longer. But the imaging capabilities of the satellites around the Earth, we can basically scan the entire planet basically every day. So we can take images at this quality, often like 1 to 2 meter resolutions of the entire Earth every single day. And that's not just like governments, there are private companies, although theirs are a bit slower. There's a geospatial imaging company who can do it in 48 hours. Every 48 hours they can do the whole planet. Pretty ridiculous. Good luck hiding from that, as you can have a bad time. But, so putting it all together, pushing towards the end here. So we know the radars can create a unique fingerprint of your size and shape using your RCS signature. They can do the same with your micro-Doppler signatures. They can do the same with your speed and overall Doppler signature. They can do the same with your polarization to figure out your material. They can do the same with high-resolution systems to figure out very precisely the physical size, lengths, and shapes of your vehicle. And they can use advanced AIs and similar systems to automatically review this, no operator involved, and decide what you are. And many systems do almost all these things, if not all of these things, simultaneously every single scan. So this is all just one pulse. That's not even discussing the next step. So, now that you're aware that they basically have you dead to rights the moment they see you, I'll leave you with a nugget of what comes next besides the missile headed your way, would be, which I have hinted at a couple times, the concept that the radar keeps looking at you. And it keeps sending pings. So not only does it see you initially, but obviously you're moving through space, so your angle is going to start changing. So they're going to start seeing you from different angles. You're going to start moving through space, so they're going to start figuring out a map of your trajectory, your speed, your Doppler histories, your time histories, your velocity histories, all that kind of stuff. And then they're going to start using statistics, and then you're screwed. Because that's really where this all comes down to. If you open these books, and like just flip to a page, it's like a 99% chance that it's just like some type of correlatory statistics. And in this case, yeah, this is statistics for amplitude receive variation. So in reality, and as you get into your fields more, and particularly if you get into like deep processing and data, it's actually all just statistics. There's no other field with statistics. That's what everything is. So don't do bad in statistics. But yes, you can use this to even further ruin the day of anyone trying to sneak past you. Right? And this can be very hard to deal with, and also very expensive to implement. But yeah, that is the end of the chat. Question and answer. I don't mind sticking around for another, as long as you guys want to ask questions, I'll sit here. I got nothing better to do. And real quick before we hit that, if you want to learn more, there are courses that you can get into. Unfortunately, being like electromagnetics, it is a lot of electrical engineering courses. I'm an electrical engineer, so I like it, but I understand that not everyone is interested in it. But courses like electromagnetic engineering, antenna design, radar systems, UH is unique in that it has a lot of classes and like entire tracks and focuses dedicated specifically to radar systems, which is not a guarantee at every single school. So it's pretty cool. This is the whole thing where I say like a lot of this stuff is classified, and like if you actually really want to work on it, you gotta like go work for like Lockheed Martin or something. I don't know, like pick your poison. Those are the books. So I did promise, yeah. These are my books.
That's your personal library?
Yes.
Oh.
All right, and then there's a sign out. If everyone would please give me feedback and give me a 1 out of 5 rating. But yep, that's everything for me. I'm good to answer questions. Otherwise, thank you all for attending. Last thing, there are 6 tech talks this semester. This is the first. The tech talks are generally on a bi-weekly cadence, although there will be slight variations. The next talk will be 3 weeks away instead of 2, because I still have to run the talk in order to record them, and I will be on work travel, so I won't be able to do it in 2 weeks, so we're going to do it in 3. The next speaker is actually here in the house. His name is Sean Mitchell. He is a senior software engineer at Cummings Aerospace, lead on multiple projects. And what is the topic you'll be discussing?
Generative AI for engineering applications.
Generative AI for engineering applications. And when you say engineering applications,
Not
example?
ChatGPT.
Not ChatGPT. All right, good, very helpful. All right, so that's the next one up. And I think when I sent out the email through the College of Engineering, I did list the other talks there. I think the next one is Chandler Kramer doing embedded programming. Then Kevin McCaffrey, Lockheed Martin engineer, doing advanced DevOps for industry. So if you're a software engineer, want to know about development operations, that kind of stuff, great resource. Then next we have you again.
I think so.
Yeah, doing, was it UAVs?
Yeah, for UAV design principles or something like that.
Yeah, principles of UAV design. And then the last talk is Jacob Hicks discussing principles of satellite communications engineering. And that's our talk series for the semester. But that's me. Thank you for attending, and it's question time.
Can you go back to the slide with the books?
Yeah. Bonk. These are great. And I guarantee, like, if you really want it, you can definitely find a PDF of these things. Like, you don't have to actually pay money. I just prefer a physical book.
So when you mentioned like how the B2 has like stuff on the top for like vents and stuff like that, I don't know the altitudes. Would a weather balloon with a like radar equipped on it be able to detect something?
It would help, maybe. Depends.
Okay.
Depends on a lot of things. Besides the fact that the B2 and other comparable vehicles, if you look at a lot of stealth drones and like intelligence, surveillance, reconnaissance drones, like for example, General Atomics recently released the Gambit series of drones. Every single one of those drones has a top inlet for the same reason. Like, why make it easier to detect you from the ground? But yes, if you have a radar from the top looking down on you, you have a better shot. But additionally, they also are making use of techniques like serpentine ducting, which is as in the entrance of the inlet does not immediately result in the engine being right there. They normally have a duct that's S-shaped to not only prevent direct, like radio wave to turbine, but also will assist in, they coat the inside in radar absorbent material, And they also make use of a technique called waveguide beyond cutoff. Depending on the frequency you're dealing with, there are physical limitations to that. But that concept is, depending on the wavelength, if you have a pipe or waveguide, which is just any type of metal tube, it could be a square, it could be a tube, whatever, that is of some proportion diameter-wise to the wavelength of the signal you're looking at, and it is of some multiple of the wavelength in terms of length, even if it's an open metal tube, the signal cannot go all the way through. It'll stop.
Okay.
So you can make use of stuff like that. Generally they don't. Generally they just use RAM, radar absorbing material, but it has been done.
The thing with deception jamming.
Yes.
So you described it as like it has to be an area larger than the actual physical target.
Its signature needs to be larger than the plane it's on to maximize its efficiency and just like deceiving.
But that does mean that no matter what, you are still visible. You're
Yes.
just lying about what you are.
You are visible, but your signature is far smaller. Generally, deception jamming is employed on advanced platforms that are stealth. So every stealth platform has a return signature. There's no such thing as an invisible plane. The radar can see it. It's just weaker, far weaker. So it'll be low level, filtering systems can reject it, and other things like that. So like what happens if you're deception jamming is generally you are there with your tiny weak signature and you're hoping they miss you. But it's way easier for them to miss you if you throw a fake big signature over here that's scary. So they're gonna focus on this thing as opposed to the sneaky little guy trying to get past.
It's to stop them from just sending a bigger missile at the big thing so that you're encapsulated in the boom.
Well, that's the trick. Deception jamming, you can make the signature look like it's anywhere.
But you have to be within the signature, don't you?
Yeah, you can make use of like cross pull and other tricks to physically, like if you are here, your deception jamming signal could be like a mile away. But your jammer's on you.
Got it.
Yeah. It's kind of nuts. There's a platform called the ADBM mauled missile that the US employs. It is a deception jamming cruise missile. And a couple were found in Ukraine. Turned out we were giving them a couple, so that's how it got popular in like known media. But that system is basically a deception jammer on a cruise missile behaving like a fancy drone. So they just launch those things, and it really helps with like SEAD operations, suppression of enemy air defenses. So like when the Ukrainians like a year or so ago had like an extremely successful bombing run that let them strike deep into Russia, they found a whole bunch of those missiles on the ground after the fact. We had basically given them the ability to make the Russians completely go after fake stuff while they just ruined everything, destroyed everything. So like it's an extremely potent capability. And like electronic warfare is one of the bases of modern military strength for a lot of reasons. Any other questions? Concerns? Interests? All right. Thank you all very much for coming.